Okay, good morning, good afternoon, good evening to everyone, and welcome to today's webinar that is entitled An Introduction to Long Axial Field of View PET Scanning. And thank you all for joining us. So we are hugely delighted to see that we've had such strong interest in this topic, which just really does reflect how rapidly that long axial field of view imaging is moving from cutting edge research into real world clinical and translational practice. So over the course of the next hour, what we'll explore is how those long axial field of view systems are going to reshape molecular imaging, from dramatically increased sensitivity through to whole body dynamic imaging, low dose protocols, faster acquisitions, and entirely new opportunities in systems biology. It's an area where physics, engineering, and clinical ambition meet. And we're very fortunate today to have three amazing speakers who sit at the heart of that intersection, representing academia, industry, and global system development. So it's my pleasure today to be able to introduce our first speaker, Professor Simon Cherry, who needs little introduction in this field. Professor Cherry is a professor at the University of California, Davis, and he now also most recently holds a position with King's College London. He is internationally leading as one of the founding pioneers of total body and long axial field of view PET imaging. He is perhaps best known as the co-developer of the Explorer total body PET scanner, a system that has fundamentally changed how the imaging community think about sensitivity, temporal resolution, and whole body kinetic imaging. Professor Cherry's work has not only driven technological innovation, but has also reframed the scientific questions that we now ask, enabling studies of whole body tracer dynamics, organ-to-organ interactions, and ultra-low dose imaging that we simply could not do before. Today, he will set the scene by discussing the scientific and technical rationale behind long axial field of view systems and discussing what they mean for research and clinical applications. Thank you, Professor Cherry, and we're looking forward to hearing from you today.
Well, hello everybody. It's a great pleasure to be here today. Good morning, good afternoon, good evening, wherever in the world you are. And so it's my job to give a little bit of an introduction to total body and long axial field of view PET, and talk about some of the capabilities and transformational potential. So in conventional PET, and I'm going to start with a little bit of background. I know we have quite an expert audience from having looked at the attendee list, but we also have some people that are fairly new to the field. So I will give a little bit of background, a little bit of the rationale for why we're doing what we're doing. So I'll start out just by talking a little bit about PET technology, the fact that we use scintillation detectors, comprising crystal scintillators that detect the high-energy photons that are emitted by our radio tracers when they decay. And those crystals are coupled to silicon photomultipliers that read out the light signal that comes out of the scintillator. So that's a detector module. And then we build these modules into rings and multiple rings around the patient, and that's what forms a conventional PET scanner that has something like the geometry that you see in the middle panel here. And then in PET imaging, what we're doing is we're looking for coincidence events. So the signature of a positron emission and decay and annihilation is that we get these back-to-back photons produced. And so these photons travel in opposite directions and reach our detectors, and that forms an event in our PET scanner. And we're looking for those two events to occur almost exactly at the same time. There is a small time difference, and we measure that, and that's called time of flight PET. And we collect many millions of these events to form a PET image through a process of image reconstruction. So that's the basics of how a conventional PET scanner works, and we combine that with a CT scanner to form a hybrid system, because we need the CT scan for anatomic information so we can better understand where our PET signals are occurring, and also to do some of the quantitative corrections for PET for photon attenuation and scatter, so that we end up with quantitative images. So if we look at clinical PET, the current status is that something on the order of about 10 million clinical scans are done a year across the world at about 10,000 different sites. Major applications are in oncology for staging, initial staging of cancer, and then monitoring response to treatment. And examples of those are shown in the image panels A and B on the right-hand side. There's also applications in cardiology and growing applications in neurology, particularly in Alzheimer's disease, where we have radio tracers specific for measuring amyloid and tau burden. Now, in oncology, we usually want to survey most or all of the body, because cancer metastasis can occur throughout the body in any of the organs. And so with a conventional scanner, we pass the patient through bed position by bed position to build up a picture of the whole body. And so this is actually extremely inefficient if you think about it, because first of all, only about 1/8 of the body is actually sitting inside the field of view of the scanner at any one moment. And secondly, a lot of the emissions of our radio tracers, when they decay, actually miss the detectors and come out the ends of the system. And so you could easily demonstrate that we collect less than 1% of the available signal being emitted by a radio tracer. So that's really poor. And also that leads to pretty noisy and pretty low spatial resolution images. And so this was the motivation behind developing total body PET. And so it's going from a conventional PET-CT scanner geometry that looks like the panel on the left to a geometry where we have detectors that really surround most or all of the body. This gives us much, much better collection efficiency, something like 20 to 60-fold higher collection efficiency for imaging the whole body than a conventional scanner. We've got really good geometric collection efficiency, and all the major organs and tissues are now in the field of view. So that gives us some really interesting opportunities, as I will show you in a moment. Of course, it comes with challenges. We know that. So challenges include the scale of the system. So now we're looking at systems that have hundreds of thousands of scintillation detectors, tens of thousands at least of channels of electronics. We've got large data sets. The raw data coming off the scanners is very large. And of course, we've got a lot more detectors, a lot more electronics. So this does mean the cost of the system is going to be significantly higher as well. So those are some of the challenges. So we got involved in this a long time ago. So about 2005, me and my colleague Ramsey Badawi were chatting away in my office one day, and we decided we were looking for a fun project to do, and we decided this would be it. You know, we thought the opportunities here were amazing, and we thought this would be a good thing to work on. I think if we'd known how long it was going to take, perhaps we'd have had second thoughts, but fortunately we were incredibly naive at the time. The other thing I'd like to say is that this was not our idea. This idea has been out in the field for decades. This is something people have talked about, thought about, the sketches, but nobody had actually done it up to this point. There were probably some good reasons for that, and we could talk about that if people are interested when we get to the Q&A. We spent a lot of time trying to raise the money to do this, and that's a story in itself as well. Did not go well for many years. A lot of turned down grant applications, both in the USA and in the UK as well. We were able to run computer simulations. It's about all we could afford to do for quite a few years. But eventually in 2015, we got a very large grant from the National Institutes of Health here in the United States that would allow us to build a complete prototype total body PET scanner. And then the big challenge was to find an industry partner to do this with, because as an academic group, there was no way we could build something on this scale by ourselves. We were successful in that eventually. And then the system was designed and built between 2016 and 18, completed in late 2018, and installed at UC Davis in 2019. So about 14 years from that first meeting to actually getting the first scan. But when we got the first scan, we were stunned. The images are just gorgeous in terms of their quality, very high signal to noise because of the fantastic counting statistics, means we can reconstruct a high spatial resolution as well. And this is a pretty standard, nothing special here, total body scan off the Explorer total body system. It's about a 310 megabecquerel injection, 7-minute scan, 60 minutes post-injection with FDG. So this now, of course, has led to quite widespread adoption. I think as people saw these images, they were very excited. We now have 4 commercially available long axial field of view or total body PET systems. There are perhaps others coming as well. And they range, as you can see, different axial lengths between 1 to almost 2 meters long. And all of these systems are just a step change from what we previously had with conventional PET. And just a little bit about naming semantics. You have this a bit awkward acronym, LAFOV. It stands for long axial field of view. Really anything above 1 meter can cover most of the organs, major organs of the body. You get some gain when you go up to almost 2 meters as well, but anything in this range is just a completely different ballpark than what we had before. So from long axial field of view or total body PET, whatever you want to call it, these systems are just amazing compared to the conventional systems that are shown in the blue that have about a 20 to 30 centimeter on average axial field of view. So I'll use the terminology total body PET because that's what I'm used to, but realize that everything I'm showing you today really can be done on any of those systems that I just mentioned. So some of the capabilities are important. So I've already mentioned the fact that we get very high quality images because we're collecting a lot more signal and we can use that to produce really high signal to noise images. But it also really opens up the parameter space for how we do PET. We can now also image very quickly. If you have a cancer patient who's in pain, can't sit still, can't lie on the bed for long, or a young child who can't stay still for long, we can scan, we can get a diagnostically acceptable image in under a minute now. So that can be very helpful in certain situations. We can also image at much lower radiation doses. So this is about 1/20th the standard injected dose, 18 megabecquerels, still diagnostically acceptable image. And so if you're doing a research project, perhaps in a chronic disease condition where you want to do multiple scans, we can now do that at very low radiation burden. And the other thing we can do is we can scan our radio tracers for much longer. So this is FDG, scan 12 hours post-injection, so that's about 6 half-lives, and still there's enough signal here to get an image. So it's really opened up the parameter space for how we acquire our data, how we trade off imaging time, radiation dose, and image quality. And we can now tailor that to the specific clinical or research need. Patient impact. So at least 500,000 and probably now closer to 1 million patients have now benefited from total body PET technology. And I'll just show you just one example where we have paired scans on a conventional scanner of a patient, and that's in the middle panel here. And this patient has a suspicious area of perhaps increased activity here. Very hard to call on the conventional scan, but on the total body scanner, same patient, just a few minutes later, we can very, very clearly see that lesion. And that's a product of having higher detection sensitivity, allowing us to reconstruct a higher spatial resolution to make that lesion very, very obvious. And there are many examples of this. So it has a very clear impact on patient management. But I want to spend the last few minutes talking about research, because here we really do have a complete game changer, because we have some unique characteristics here of total body PET. So on the right is sort of our standard clinical scan, 7 minutes long. But we can also scan much more quickly, as I mentioned. And even in 1 second, we get a fairly acceptable image of the entire human body with total body PET. And if you can scan the body in 1 second, that means you can scan the body every second. And you can watch as you inject your radioactive tracer into the body, and you can watch its distribution across the body over time. And that's what's shown in this movie here. And when we first saw this was probably the aha moment, because this had never been possible before with medical imaging. And now we have the means to do this. And when we marry this with advanced computational tools, there's a huge amount of information we can extract from a dynamic sequence of PET images. And I'll just illustrate that with a couple of examples in a moment. So underlying that video, which is very nice to watch, is quantitative data. So from every tissue and organ of the body, we can measure the time activity curve, so the activity concentration of the radio tracer as a function of time. We can actually measure in every single voxel in the body. So we can actually have 1 million of these time activity curves to analyze. So let me show you a simple example of that, and that would be total body perfusion imaging. And this is with a radio tracer carbon-11 butanol, which is a freely diffusible tracer. The modeling for this is quite straightforward. We have a 2-compartment kinetic model. The tracer is either in the blood or it's in the tissue, and there's exchange rate between the 2 compartments, K1, and that is the perfusion. And so we model that dynamic data to measure perfusion quantitatively. So these images in the center panel here are not maps of uptake, they are maps of perfusion or tissue flow in units of milliliters of blood per minute per cubic centimeters, fully quantitatively modeled. And this is a paired study where we're actually sort of doing a total body activation paradigm. So we have the subject at rest on the right-hand side, and then we do a second scan where we impose a physiological stress test on the subject, which in this case was putting their feet into ice cold water while we were injecting, which invoked a stress to the system, widespread changes in perfusion, and we can measure that in every organ of the body. We see changes, not surprisingly, in the musculature, in the limbs. We see changes in myocardial perfusion, and we see regional changes in brain perfusion as well. We can map all of that out. And I think this paradigm of activation studies with a baseline and some kind of intervention is a really exciting opportunity for total body PET research. My second example and final example is in immunological imaging. So imaging of the immune system is something that's a very exciting opportunity. The immune system is involved in our response to almost every disease and disorder there is. This is a small molecule labeled with fluorine 18 that is selective for activated T cells. And so this tracer comes into the tissue. It can be phosphorylated and trapped in the tissue, but it can also be dephosphorylated and come back out. And in activated T cells, we see increased phosphorylation, decreased dephosphorylation, which means we see an accumulation of this radio tracer in activated T cells, and we can measure that throughout the body with PET. The model we apply here, the computational models, are quite a bit more complicated, but the component that we're very interested in measuring is this K3 parameter here, which is the amount of phosphorylation of this tracer that's going on in the cells. And so here's an example of using it to look at cancer immunotherapy. So on the left-hand side is the image of the radio tracer uptake, and I'm drawing your attention here to all the lymph nodes that we can beautifully see in this high-resolution image. And if I just look at uptake, and I look at this patient, and I look at the uptake of this tracer in the lymph nodes before therapy and after therapy, you see this very mixed picture. It's very hard to see across these different lymph nodes that there's much consistency. And that's because we really haven't modeled the data here. If I now do the full kinetic modeling, which really accounts for the delivery of the tracer into the tissue as well, and I look at that parameter K3 in each of these lymph nodes, now we see a very clear pattern where post-therapy, after giving immunotherapy, we see increased phosphorylation, increased activity of T cells in these lymph nodes. And so by doing this modeling, we can look at T cell activation in peripheral lymph nodes with cancer immunotherapy. And I think it's a beautiful example of where the extended axial field of view allows you to assess all the lymph nodes with high sensitivity, dynamic imaging. This would not have been possible on conventional scanners. So to summarize, PET's a very sensitive technique where we can measure physiology, metabolism, molecular targets. Total body and long axial field of view allows us to get shorter clinical scans, reduce our radiation burden, and or improve our image quality. We can now measure radiotracer kinetics in the research setting across the entire body with a temporal resolution of as good as 1 second. That opens up lots of opportunities for studying the human body as a system in health and disease. Of course, I'm just the spokesperson for a huge team of people behind this. A large team at UC Davis who have developed a lot of this methodology. Over the last several years, we've had the scanner. An amazing team at United Imaging that helped us realize our dream to build the first total body system. And if you're interested in this topic and learning more about it, I want to draw your attention to the fact that the third Total Body PET conference is coming up this year in September at UC Davis, where we'll be talking about imaging the dynamics of life. The abstract deadline is February 15th. You still have time to submit an abstract, and I hope to see many of you in California later this year. And with that, thank you very much.
Thanks, Simon. That was a great presentation, and thank you for that. Please do post your questions in the Q&A, and we'll have time for that at the end of our third presentation. So it's my pleasure now to introduce our second speaker, Dr. Stewart Young from United Imaging. Dr. Young has extensive experience across both PET and hybrid imaging system development, and he works with a company that has been highly active in advancing that long axial field of view PET system at scale, as we have already seen. And United Imaging has been at the forefront of deploying those extended and total body PET systems internationally. And Dr. Young brings that valuable insight into the implementation of these systems' performance, but also that early clinical experience across a range of applications. He will be sharing his perspectives today on how long axial field of view imaging is being adopted globally and what we're learning from those early users and where the technology is heading next. So it's my pleasure to hand over.
Thank you, Juliana. It's my pleasure to have the microphone for the next 15 minutes or so. Thank you very much for, I'm going to talk a little bit here about the introduction of LAFOV PET and capabilities and transformational potential. So as Juliana has introduced myself, I'm from the Research Collaborations team in Europe here in United Imaging. So long axis field of view PET. Let's talk a little bit about the milestone, which was beautifully introduced by Simon. It's a pleasure to follow such a wonderful talk. This is really just I think repeating the principles that Simon has introduced in terms of extending the detectors all the way along the body and increasing the sensitivity. Just here highlighting how you can all of the lines of response. You can integrate the signal all the way across the body at the same time and basically gain a huge degree of sensitivity in detecting these beautiful PET images, which we're going to spend a bit of time now looking at. So the full coverage of coincidences really just enables the high system sensitivity. Here a number comparing to a conventional 24 centimeter axial field of view system. We've had a beautiful introduction. I'm not just going to briefly repeat. I'm going to give it the tagline of sort of landing on the moon, which Simon has just introduced to us, and how it was done. He beautifully described the pain of all the grant applications. I sort of shortened the story here to when United Imaging came on board in 2016 to the Explorer Consortium, and within a short space of time of 3 years was able to put the Explorer Consortium together the scanner that created the first clinical scans in 2019, and sort of really. I gave it the tagline here, landing on the moon, putting the first footprint on the moon, and sort of Apollo 11 moment for the field of long axis field of view PET imaging. A landmark, and then moving on to sort of from Apollo 11, I guess, to sort of Apollo 17. Of course, the system started to roll out across the world. Here an example of one of the people using the U-Explorer system in Bologna, Professor Fanti. And really he's taking his moon buggy and going out across the moon and really discovering using it to discover so many things about oncology of the prostate and all of the therapies that can be done here. An example of starting up the use of lutetium PSMA therapy, and also some results published this year last year in the JNM by Farolfi et al. About the tracking and the use of PET CT and the long axis field of view PET CT to track the response of CAR T therapy in lymphoma patients. So just taking the potential really and going with it as fast as possible, and having fun bouncing over this new and unexplored surface of the moon. Simon has also really just wonderfully showcased about the parameter space. So what I want to do here is just walk around that parameter space a bit and give some more examples of how we can see more with improved quality, how we can improve outcomes and reduce the dose, and and achieve faster and more confident diagnosis using long-axis field of view PET systems. So the first example here comes from one of our users of the next generation of PET-CT systems, the Panorama GS, Dr. Frank Bengel in Germany. And what you can see here is a comparison of a short-axis field of view system using the OSEM reconstruction, 15 minutes of data integrated together. And this is just showing you the sort of how you can really cut that time down. So this is what you could achieve with an OSEM reconstruction, the same parameters at 5 minutes, 2.5 minutes. You can see some more noise appearing at about 1 minute, even down to 30 seconds. And even at 15 seconds, it's arguable that you're also still more or less comparable to 15 minutes. So I think just repeating again what Simon said and really showcasing it with some clear images here. And now we are not on the moon anymore. We're in a Ferrari car with the next generation of taking all of the learnings of the first generation of systems and putting it all together and throwing everything that you can get to stick at the wall. This is the tracer toolbox that was acquired by Dr. Bengel in the first 3 or 4 weeks of having his scanner. Just showing everything everybody knows about FEG in our field, and PSMA and dotatate is coming everywhere. Here are some examples of the FAPI tracer and perfusion imaging using oxygen 15 water to image the blood flow. And of course also some immune cell imaging. So just fantastic images and showing off the capabilities of the system. Here, the next thing that you can do, I think, is you can also just add on a layer just to demonstrate again the power of AI-based reconstruction. Here, the 15-minute OSEM on a short axis field of view. And down here we have with AI-based reconstruction the same more or less image quality in 15 seconds, or with the OSEM over 15 seconds, or even over 5 minutes with the OSEM with this huge increase of the amount of signal in the images. This is a sort of stripped down. I tried to take all of the corporate out of this. I just wanted to mention that there's sort of another, of course, the advantage of having these huge cameras and long cameras is that you can, of course, also just simply learn the characteristics of your data with extremely high accuracy. And then capture that, in this case, in an algorithm that we call the DPR, which is AI-based reconstruction, is trained with data from these long-axis systems, which are acquired under optimal conditions, and you can apply those learnings from the data distributions and the noise distributions to achieve and to sort of deploy this image quality to systems with different characteristics, so shorter axial field of view or different detector configurations, etc., etc., etc. So yeah, using not only does it have its own inherent worth of having these long axis systems, but it also enables us to sort of trickle down the knowledge of the data that we're acquiring into the rest of the fleet, even existing scanners out in the field. So AI-based reconstruction is the next thing on the field. But I also wanted to say very briefly here, like, where's long axis field of view going next? We've talked about the Explorer system and the Panorama system, but what about in between? So I think this is what's starting to happen as well. These systems are, of course, fantastic. They come with their own price tag. So finding the sweet spot in the middle of this spectrum of axial field of view length is not everyone's going to make the same choices. So finding the right fit is the title of this slide. And just to say that I think that's the next stage, is to explore this space of possibilities, not only in all of the parameters of what you can change in terms of dose and in terms of noise, but just in terms of the length of the system as well. So let's see what happens in the future in this space of long axis or medium axis or short axis field of view PET imaging. And this is just to say that you can also imagine systems that will be on a scalable platform. So you can start with smaller systems and have exactly the same system, just extending the field of view all the way up to the 1 meter 48 or the 2 meter system. So yeah. Okay, going back around the paddock and looking a little bit more at the parameter space, we're looking again here just at some examples of shortening the field of the frame duration around from 300 seconds all the way down to 5 seconds. You can see that okay, this noise starts to creep in, but you can as Simon said already, you can start to get wonderful and usable images even after 5 seconds or 1 second if you're doing dynamic imaging as well. This is another example of just underlying the point, I think, about this is about a pediatric image, of course, with a child moving. So motion management and motion correction. First of all, just imaging over a shorter period of time makes a significant contribution to motion management, but also, of course, just reducing the dose. And there are strategies you can apply to even further manage the motion. So problems which were enormous problems in the past are beginning to get a handle on these problems and manage them. And long axis field of view systems is really paying a major contribution to that. So here a nice example of just how you can leverage this new parameter space to solve problems. We also saw an example of long delay imaging over up to 6 half-lives. This is just to make the same point, I think, and really show some examples. These are both with FDG imaging, but of course there are isotopes with different properties where you can really go far out in this space and explore the scope. I think this is even though the systems have been around for 5 or 6 years, there's still plenty of territory to be explored on this axis. I'm just looking at the time, so I'm going to start wrapping it up. Last part of my talk, I'm just going to very briefly touch on a couple of the transformational potentials around in terms of research. We've already had a feeling about the dynamic imaging and the tracer development. So the whole body coverage enables high resolution dynamic imaging. And there's a parametric analysis of this data is a fundamental a tool in the toolkit for making the maximum of the research potential of these systems for sure. So optimization of imaging times for new drugs, we saw already an example of that. Low injected dose for translational research and kinetic characterization of all different kind of radioligands. Here's an example of that in the theranostic space. So how the gallium PSMA PET dynamics are able to be explored very beautifully with this system here. Total body parametric imaging. I'm going to just go to the last slide and I think mention another exciting area. Of course, the fact that you have the entire body in the field of view enables that you can correlate signals across the time course of these images in a very beautiful way. So investigating the brain-body axis is clearly an exciting potential of this technology. Positive correlations are identified, for example, here in patients with Parkinson's disease. But also on the right, another example of the correlation between adipose tissue uptake and brain aging. So really, again, just so much space to explore and discover things about the body that we have not been able to simply to investigate or under very difficult conditions in the past. Okay, in view of time, I'm going to push it towards the end here, summarizing. The long axis field of view PET is transforming the parameter space of PET imaging, offering improved image quality at lower doses and shorter imaging times. and the exploration of the transformational possibilities has really only just begun. Thank you very much.
Thanks,
I'll pass it
Stewart.
back.
That was brilliant. And please, everyone, do keep putting your questions into the Q&A. We will have time after our third and final speaker. So our third and final speaker for today is Dr. Antonis Kalemis from Siemens Healthineers. Antonis is a leading expert in PET system design and innovation, and he's played a key role in the development of advanced PET technologies within one of the world's foremost medical imaging companies. At Siemens Healthineers, he's been closely involved in pushing the boundaries of that detector design, system sensitivity, and scalable axial field of view solutions. And he helps build that gap between academic prototypes and robust clinically deployable systems. And Dr. Kalemis in our third presentation will bring that industry and engineering perspective, discussing how those long axial field of view concepts are being translated into commercial platforms. So thank you very much, and I look forward to handing over to our third and final presentation for today.
Good evening, good morning from my side, wherever you are. First of all, can you see my image, my screen? Yes, yeah, great. So I'll start my presentation with one question, and I'll try to give a positive response to the question. So the question basically is the all-time classic, to be or not to be, and that is, in our situation, more about whether to be a user of a large axial field of view system or not. The real boundary of acquiring a large axial field of view system is not necessarily any longer the technology, as we have heard before in the previous presentations. It's more about the cost of the system and about both the acquisition cost of the system and the operating cost of the system, as well as other concerns that might come as well together. And many of people who might think that this is impossible. And for that, I'll have another quote to put forward, and that is that nothing is impossible, especially when there is a lot of people currently that have been utilizing the system, have tried to implement the system into the clinical research practice. And we're talking just from Siemens' perspective about 55 sites, and some of them even have 2 quadras being installed. I'm pretty sure that this is only one part of the image. United Imaging and now even GE has also to present additional substantial additional number to these 55 sites that we have here. Simon said about 500,000 scans overall, if I remember correctly. 195,000 of those scans is definitely done on the quadras. People are using the systems both for clinical as well as for academic research. And from the point of view of adopting the system, the real benefit of, if you want to summarize it in one thing, is the economy of scale. And scale in this case means large axial field of view. There are basically sites that they have decided to go for this system, for this kind of systems, in order to address even space limitations. So trying to reduce the number of PET-CT scanners from 2 to 1. And also other sites upgraded from standard axial field of view systems. Obviously, that's the case for the majority of the sites that I'm familiar with, into large axial field of view. And this is also possible just because of many of those systems don't really need more space. You can put a large axial field of view system in the same space that you had for a standard axial field of view system, like the one here that I present from Bern in Switzerland. And of course, the other economy of scale is reducing personnel shortages. Of course, how this is done purely by going from a 2-scanner site into a single scanner site. Of course, this imposes additional strains on the personnel that should not be omitted, and this have today answers through advanced technologies. Some of those, like the ones that Stewart presented before. And then the other thing, the other angle that one can see to that is basically efficient use of activity and time. Nothing new from what Simon and Young and Stewart presented before. It's just a matter of how you utilize the amount of activity that you have either from your own cyclotron per day or the activity that you buy, and how many scans you can do with this activity, and also how much of the operating time that you have in your practice, and how many patients can squeeze into this operational time. And these particular systems, this was anyway the question that we could answer by improving the technology in the standard axial field of view systems as well. But these new systems, as has been shown before, they can do both. So you can have shorter acquisition times, and you can have also less activity. And that's also how sites, as I said before, persuaded themselves and their procurement offices, and they basically adopted not only one but more than one large axial field of view systems. We have in our install base 2 at the moment, and there are like 3, if I remember correctly, that are coming up shortly. So going into the actual utilization of the system, as Stewart said before, and Simon, you can expand your offering of what your department can do. Now we can do pediatrics, and we can even have one site in 2 sites in Europe that they do pregnant patients. They can offer the service for pregnant patients when this is needed, when this is absolutely necessary. Before it was out of the question. Today it's not, because of this technology. We started discussing about surveillance or screening. So sites. We have sites that they are exploring this area of potentially using the large axial field of view PET-CT systems for critical population that they need surveillance for specific conditions. And of course, it's the whole expansion to non-oncological patients where dose is important. The reduction of dose is important. And of course, all this can be done with improved image quality because of the additional sensitivity and the technology that these systems bring in, and of course, improved quantification. This essentially has the potential, or actually has demonstrated, that brings the PET-CT of the PET of the old days, where PET was completely quantitative and it was utilized for research purposes, now into the clinic, and being able to utilize these concepts where has been identified 25, 30 years before, but now in real time into the clinic. Just a very simple example with 3 examples which are not different from what the other presenters have shown. As I said, you can do infant imaging by eliminating sedation, which was one of the most important concerns, but also dose. For pediatric imaging, you can define flexible protocols which they even incorporate dual isotopes. So, for example, here is an isotope with PSMA, a protocol with PSMA and FDG and we see here some liver metastasis from prostate cancer. And of course, you can also improve the image quality and the quantification for radioisotopes that were utilized before, but the image quality was very, very difficult to be optimized. And moving this sort of concepts from the clinic into research and expanding, these new devices have the ability to reshape the concept of PET physics. They have the ability to to support and expedite drug development, which is something that has been tried before with not so much success. Now I think that this new technology has gives an extra wind for this area to be explored again. And of course, we can probe into novel clinical concepts and different areas. And with that, I'll start with what I said before. Let's think about dual tracer imaging into a single PET scan. Here is again a different application that utilizes FTG and FAPI. This is protocol-based. This is utilizing the enhanced sensitivity of the system and the speed of the system to inject in different time points, take advantage of the different kinetics and, well, in this case, kinetics of the traces, and separate the two traces from one another. But this is not the end of the story, it's rather the beginning, because we can now also start thinking about other solutions. So we can think about PET physics radioisotope separation. So utilize the ability of detecting double and triple acquisitions to separate those, for example, two traces that are, one is pure positron emitter and the other one is not only a positron emitter but also an additional gamma emitter. And by this you can separate the two isotopes from one another, and also the traces from one another. Is that unique for large axial PET of large axial field of view systems? No, it's not. But what the large axial field of view PET CT systems offer is, with their additional sensitivity, it is easier to detect those coincidences with a very, very low yield and have a substantially better image quality that was before. And this image quality can be interpreted into a more accurate quantification of those traces. And that's, again, this is just example. These are just examples. Another example, which I'm not here, is making use of this physics-based separation to also further go and, for example, identify other applications. So, like, for example, orthopositronium live imaging. This is another very, very hot topic at the moment in the community, where you can essentially identify orthopositronium generation, which has a very low probability, but it has a very interesting property, which is that it changes the lifetime expectancy by the amount of the pH in the environment that is generated. And by doing this, you can, for example, identify hypoxic parts of the lesion versus non-hypoxic. There are a fair few papers already in the literature. More is coming up, and it's as I said, it's not something that can be done only with large axial field of view systems, but the large sensitivity of these systems enable the more accurate identification, separation of the isotopes, and ultimately, most likely, the only viable clinical solution utilizing these concepts. Stewart, I think, said about combining or interrogating the connection between different parts of the body. We knew for quite some time the heart-brain axis. We knew also for example, the brain-gut axis. Now it is able, with these systems, having all vital organs in the field of view, to not only identify the activity in those organs, but also bring models or generate models that interrogate and present in a more holistic way these results and reason why certain diseases have the phenotype that we see and we couldn't understand before. Kinetic modeling, as both Simon and Stewart said earlier, is something that it is possible. Actually, it lends itself very nicely with this large axial field of view system because of the increased sensitivity and because of the full body coverage. There are tools at the moment that you can utilize this into the clinic. There are clinical users of large axial PET CT systems that they use this clinically wherever it makes sense, but it also allows itself for drug development. If you're able to automate the full multi-parametric PET and basically reduce the whole arduous process of blood sampling, dynamic acquisition, denoising, implementing kinetic models into different platforms, into one-stop shop, ideally by pressing only one button, and also reducing the demand from 1 hour scans into something like 20 minutes, which is currently today available with population-based input function, having all the organs within the same field of view. It basically makes this very, very easy for academic research, for clinical use, but also, as importantly, for drug development. And my last slide is about expanding the boundary. So this is an example from a publication from Turku PET Center, where they were trying, by using oxygen perfusion, whole body imaging, to identify signatures of behavior, signature of feelings. This is nothing close to the clinic yet, but this is just a window of what is possible in the future with this kind of systems. And I will leave you by one quote from Professor Rodney Hicks, which I found it very, very inspiring. And this is, he said at some point that having seen some incredible advances in PET in my over 30 years involvement in the field, I feel that seldom has the overused term game changer been more appropriate. And I think that I really share the feeling with him about this. We have been working together with clinicians for a long period of time. We only now start with this system, start seeing the clear development and opening the windows bright in the area of nuclear medicine after at least not 30 years for me, but definitely 20 years with my involvement in the field. And with that, I'd like to thank you very much for your attendance. Thank you.
Thanks, Antonis. And thank you, everyone. It's been fantastic to hear those three presentations and just really follow through the scientific origins, the engineering of the systems, the commercializations, and actually deploying and demonstrating its future potential. So yes, I'm very proud to be here with you all today. I think we've got a couple of minutes for some questions that are still, Simon's did a great job of answering some of those Q&As actually within the piece. But I guess the first question that's come through, which total body PET is going to be instrumental for this, is in terms of therapeutic radiopharmaceutical therapy and dosimetry. I guess both beta and alpha dosimetry with multiple time points. How do you think that total body PET can help drive this forward as we see those the growth and opportunities of those therapeutic radionuclides? So I don't know who wants to take that from our panel.
I guess I can say a quick word, which is that, I think the image quality with total body PET really allows you to assess, the degree to which the target you're trying to treat is present, and also the disease burden so much better than before across the entire body. So I think that's great. A difficulty, though, is that still a lot of the therapeutic radionuclides that we want to use don't emit positrons, of course. So we have companion diagnostics in some cases, but I think SPECT will continue to be important in this area as well. So we should not lose sight of the fact that high quality quantitative spec systems will also be very important for radionuclide therapy, along with total body PET, in my opinion.
Fantastic. Thanks, Simon.
Can I just add that from our experience, what we have seen is that also what Stewart said before, that you have now the ability to scan longer from the injected activity. This gives you the ability of reducing the background and basically just image much better the signal from the background. And this in a situation like PSMA, for example, which is utilized as gallium PSMA or fluorinated PSMA, which is a companion diagnostic for the lutetium or actinium PSMA, I think that this gives much more confidence, both for the identification of the receptors, for the planning of the therapy, as well as for conclusive or better identification of success or failure of the therapy. Just as an example.
Yeah. Absolutely. I guess I can also add in simply that the doses that need to be applied to discover things about the patient are coming down at a rapid rate, and therefore, there's potential to image more often in the follow-up in these patient populations potentially as well.
Thank you. Yeah, it's really exciting. And yeah, lots of innovation to come, I think, isn't there? So
Yes.
I have a few questions that we've already answered, and I guess data has always been something that's kind of come through at the forefront of how we can manage those kind of data sets. So one of the key outputs from NPIP as a program and platform this year as well will be to create that centralized data platform. So I was just intrigued to hear from the panel, what do you see as the benefits of having that centralized data platform, and how can that interact with the network, I guess, that we're trying to create, both from a UK perspective, but also internationally as a whole?
Well, I think sharing of data is really important, right? I mean, there's still relatively few of these systems around. And while the field's growing greatly, it's still not going to be everywhere. And so, the ability to share data and pool data across sites as well to give us a lot more power in understanding the distributions in different populations is hugely important. So there are a lot of challenges in doing this, I know, but I think the community seems very interested and enthusiastic to do this, and I think it will allow us to answer questions that none of us can answer on our own. So it's really important in my view.
I can only... Please, Antonis, go ahead.
No, I was about to say that from painful personal experience working with data protection, I think that it's something that it's definitely not possible from a manufacturer side. So an initiative like NPIP, I think it's paramount to be able to not only collect the data, but also securely distribute and monitor who uses the data and how, because this is the only way, unfortunately, the current data protection environment that this kind of application can work. So I think that it's an excellent initiative, and I only suggest that you continue going forward with that. Agree
completely. I think it fulfills a huge need in our community, and yeah, I think more eyes on data, and we are simply at the beginning of an age of exploration. So sharing is critical.
So there's a couple more questions in the question and answer, but we are running out of time now. I can see Simon's doing a great job of answering those as well in the background. So it's just left, I guess, for us to say thank you to everybody for joining. It's been a really, really fascinating webinar, and delighted to have such representation from the community, and we're looking forward to hearing lots more in the series.
Our pleasure. Thank you for inviting us.
Thanks very much. Thanks, everyone.
Thank you for the invitation.